In the previous video, we graphed the heating curve of water, and we defined the heat of fusion, specific heat, heat of vaporization. So if you're not familiar with those concepts, I recommend going back and watching that video first, because you will need to be familiar with the heating curve of water to solve this problem. So in this problem, we're looking at combined energy calculations, and we need to dissect which processes are occurring and which equations we need to use to be able to solve this. So the problem says an athlete lifted weights and has a sore arm. An ice bag is filled with 125 grams of ice at 0 degrees Celsius. How much heat in kilojoules is absorbed to melt the ice and reach body temperature? And the body temperature of humans is about 37 degrees Celsius. So whenever I encounter this type of problem is first identify where are we starting? What phases do we have and what do we need to do in this process? So the first thing it tells us is that we have ice at 0 degrees Celsius. So I like to just doodle myself a little picture. So we have, okay, these are going to be terrible ice cubes, but we have some ice, and that ice is at 0 degrees Celsius. Now, ultimately, it's telling us we need to melt that ice, and then it needs to reach the body temperature, which is 37 degrees Celsius. So the first thing we have to do is melt the ice. And once we do that, we are going to have water. So here we have water. Now keep in mind, and this is where the heating curve comes in very helpful, is that we're starting with ice. So we're in this phase, and it is at 0 degrees Celsius. So we're actually right here. And the first step that we need to do is melt that ice. Now remember that when we have a phase change, the temperature is not actually changing. So we started at 0 degrees Celsius, we're melting the ice, and as soon as that ice melts, it is still at 0 degrees Celsius before we apply more heat. So that water initially is going to be at 0 degrees Celsius. Now, once we've melted that water, the next step will be to heat that water to 37 degrees Celsius, which is the body temperature of humans. So now we are looking at this region of the heating curve. We have melted the ice, we have water, and that water is heating up to 37. And remember that when we don't have a phase change, so here the phase is not changing, it's water, but it's going from cold water at 0 degrees Celsius to pretty warm water at 37. And for that, we will need to use the Q equals mc delta T equation. So in the second step of the process, we are heating water. So here there is no phase change. I'm going to end up with the exact same picture. The only difference is that the temperature changed, and now that temperature is 37 degrees Celsius. So this is going to be a two-step process, and we need to use two equations, and we're going to add those up at the very end. So in the melting process, we do have a phase change. So we're looking at the delta H fusion equation. So while we are melting ice, we want Q equals M times the heat of fusion. And when we are heating water, we don't have a phase change. We want the Q equals mc delta T equation. And that is probably the hardest part of this battle. Once you've figured out where you are in the heating curve and which equations you need, then it's really just a matter of plugging in the correct values and keeping track of units. Okay, so I'm going to call these Q1 and Q2 just so I can kind of keep track of what I'm calculating. So Q1 will be mass times the heat of fusion. And the mass will just come directly from the problem. It looks like we have 125 grams of ice. So our mass is 125. And make sure you include units on everything. Now, the heat of fusion of water is a value that you would just look up. So if you recall from previous videos, there were two different values that we used. Keep in mind that the problem is asking us to solve this in kilojoules. So I want the value of the heat of fusion that's expressed in joules, just because it makes life a little bit easier. I don't have to convert any units. So the heat of fusion is 334 joules per gram. And I always recommend that you don't write units with a little slash because it makes it difficult to see which units cancel. If you make it a nice line and make it look like a fraction, well, now we see that we have grams on the top and grams on the bottom, so those units will cancel nicely. And that's exactly what we want because heat needs to be expressed in joules or kilojoules or some sort of unit of energy. We don't want grams in there. Now the problem is asking us to leave the answer in kilojoules. So you could convert this at the very end, or we could add an extra step here and make sure we convert those joules to kilojoules. So the prefix kilo means 10 to the 3, which means that there are 10 to the 3 joules in 1 kilojoule. Or you could say 1,000 joules in 1 kilojoule. So here I want to get rid of joules. And if joules are in the numerator, well, in order for that to cancel, they need to be in the denominator. So there are 1,000 joules in 1 kilojoule, and that problem is now set up. So we see that grams will cancel, joules will cancel, and our answer will be left in kilojoules. And then I'm going to plug everything in, and that will give me my value for Q1. Okay, and I'm glad I converted to kilojoules because otherwise this would have been a pretty large number. So I'm getting 41.75 kilojoules. I'm not worried about significant figures right now. I'm going to deal with that at the very end. So we'll just leave it the way that it is. Okay, let's calculate Q2. So we said in Q2 we don't have a phase change, so we're using the MC delta T equation, which means we need to calculate the change in temperature. So the change in temperature will be the final temperature minus the initial temperature. And here it's very straightforward because our final temperature is 37 degrees Celsius, but the initial temperature is 0. So really we didn't need to do that calculation, but you can just to be very clear on where the numbers come from. So that delta T is 37 degrees Celsius. The mass is the same. We're using 125 grams of that sample. We need the specific heat of water, and that's also a value that we would just look up in a table. But keep in mind, because we want the units to be in kilojoules, I want the specific heat that's expressed in joules. And the specific heat of water is 4.184 joules per gram per degree Celsius. Then I'm going to plug in my change in temperature, which is 37 degrees Celsius. And the last thing I need to do is convert that to kilojoules. So maybe I'll just extend this line to make it a little bit easier to see. And again, joules are listed in the numerator, so I need them to be in the denominator to cancel. So there are 1,000 joules in 1 kilojoule, and everything is now set up and ready to go. Grams are diagonal, they cancel. We have Celsius in the numerator and the denominator, those cancel. Then we have joules in the numerator and the denominator, those cancel, which means at the end we're left in kilojoules, which is exactly what we're trying to find. And then I'm going to plug that in. And I'm getting 19.35 kilojoules. Okay, so we're not finished. We do need to add those values together because the problem is asking us for total heat. It wants heat for this entire process, both melting and the warming up of water. So the total heat will be these two values added together. And that gives me 61.1 kilojoules. And then I'll just take a look at the sig figs. It looks like we should be keeping about 2 sig figs, so I will call this 61 kilojoules.